A spacecraft the size of a school bus just flew past a lump of rock in the asteroid belt. And what it found there made scientists rewrite what they thought they understood about how planets are born. Stick with me, because I'm about to walk you through exactly what NASA's Lucy mission just confirmed. And by the end, you'll understand why researchers are calling this one of the strangest small worlds ever examined up close. And if you like getting real space discoveries without the hype, go ahead and subscribe now, because this channel breaks things down using nothing but published research and mission data. Let's start with why this mission exists in the first place, because the backstory matters more than most people realize. Back in 2016, NASA selected a new mission under its Discovery program, a category built for lower cost, faster turnaround projects that still deliver serious science. They named it Lucy, after the famous 3.2 million year old human ancestor fossil discovered in Ethiopia in 1974, because just as that fossil helped researchers understand the origins of humanity, this spacecraft was designed to help researchers understand the origins of our solar system. The target wasn't Mars, or the Moon, or anywhere close to home. The target was a strange population of asteroids that share Jupiter's orbit around the Sun, clustered into two massive swarms, one trailing ahead of the planet and one following behind. These are called the Jupiter Trojans, and nothing had ever visited them before. Not once in the entire history of space exploration. Scientists believe these objects are basically frozen time capsules, leftover material from the earliest days of the solar system, never fully melted down or reprocessed the way material closer to the Sun has been. If you want to know what the building blocks of the planets actually looked like 4.5 billion years ago, the Trojans are about as close as you can get without inventing a time machine. Lucy launched in October of 2021, and here's where the design of this mission gets genuinely wild. Because of how the spacecraft's trajectory works, it isn't visiting one or two targets. It's flying past 8 different small worlds across 12 years, using multiple gravity assists from Earth to slingshot itself further out each time. That's more individual objects than any single spacecraft in history has ever visited. Along the way, before it even reaches its main targets, the mission planners realized Lucy would pass close enough to a couple of asteroids in the main belt to justify bonus flybys. Nobody expected those detours to become some of the most talked about discoveries of the entire mission. But that's exactly what happened. The first surprise came in November of 2023, when Lucy swept past a small asteroid called Dinkinesh, a name that, fittingly, is the Ethiopian name for the Lucy fossil itself. Ground-based telescopes had shown Dinkinesh as nothing more than a tiny point of light, roughly half a mile across, unremarkable in every way. Then the spacecraft got close, and the images started coming back, and researchers noticed something in the data that shouldn't have been there. A second, much smaller object was sitting right next to it. Dinkinesh had a moon, and not just an ordinary moon either. Follow-up analysis published afterward showed that this tiny satellite, later named Selam, was itself what's called a contact binary, meaning it's actually two separate lobes gently touching each other. Essentially two miniature worlds stuck together like a snowman, quietly orbiting a slightly larger asteroid nobody had paid much attention to before. Finding a satellite at all was already a bonus. Finding out that satellite was itself a two-lobed contact binary was the kind of detail that made planetary scientists sit up in their chairs. Because it hints that these small, gently colliding, slowly merging objects might be far more common throughout the asteroid belt than anyone had assumed. Comment down below if you've ever heard of a moon orbiting an asteroid having its own two-part structure, because honestly, most people haven't. And it's one of those details that quietly rewrites the textbook. Then came April 20th of 2025, and this is the flyby that really deserves the word discovery. Lucy's next scheduled target on its long road toward Jupiter was a main belt asteroid called Donaldjohanson, named after the paleoanthropologist who discovered the original Lucy fossil back in the 1970s. Ground-based observations before the flyby had already hinted that this object was elongated and slow spinning, rotating once every roughly 10.5 days, which is unusually leisurely for a body of its size. Nobody expected much more detail than that. Then, Lucy passed within about 650 miles of the surface, and the images that came back showed something nobody was prepared for. Donaldjohanson isn't a simple rock. It's peanut-shaped, made of two distinct lobes connected by a narrower neck, the kind of shape that forms when material from a shattered parent body slowly drifts back together after a violent ancient collision. Researchers estimate that collision happened around 155 million years ago, meaning this object has been quietly reassembling itself and drifting through the inner solar system since roughly the age of the dinosaurs. But the shape alone wasn't the strange part. The way it moves through space was most asteroids and planets spin cleanly around a single axis, the same simple rotation you'd expect from a top spinning on a table. Donaldjohanson doesn't do that. Instead, Lucy's instruments confirmed it's tumbling through what's called non-principal axis rotation, essentially wobbling on two axes at once rather than spinning smoothly around one. It rotates end over end roughly every 10.5 days, while simultaneously nodding back and forth along its long axis on a separate, slower cycle. Picture a badly thrown football wobbling end over end through the air, except this wobble has been going on continuously for millions of years in the vacuum of space. Ground-based telescopes had picked up the basic 10.5-day rotation period, but the second, hidden wobble was completely invisible until Lucy got close enough to actually see it. Scientists working on the mission believe they know what's driving that wobble, and the explanation itself is almost as strange as the wobble. It's called the YORP effect, named after the four researchers who first identified it, and it works through something you'd never expect to matter at all, which is sunlight. As the sun warms one side of an irregularly shaped object, that side eventually radiates the absorbed heat back out into space as infrared light. That radiation carries away a tiny, tiny amount of momentum, giving the asteroid an almost imperceptible recoil, similar to the way exhaust pushes back on a rocket, just unimaginably weaker. On a perfectly symmetrical, smooth object, these tiny recoils from different areas would cancel each other out completely. But Donaldjohanson isn't symmetrical. It's lumpy, peanut-shaped, and uneven, so those recoils don't cancel out. Instead, they accumulate, slowly, patiently over millions of years, gradually altering the object's spin. Researchers now estimate that when Donaldjohanson first formed, it was likely spinning at least 10 times faster than it does today, and that over roughly the last 20 to 60 million years, sunlight alone has been quietly breaking its rotation down to the strange, wobbling state Lucy observed. It's worth pausing on that for a second, because we're talking about a process powered entirely by photons, gradually reshaping the spin of a mountain-sized object across geological timescales, with no engine, no collision, nothing but light hitting rock. That same slowdown left physical scars on the surface too. As the rotation eased and the balance between gravity and centrifugal force shifted, loose rock and debris on the asteroid's neck. Region began sliding downhill, gradually smoothing out craters and building up a visible ridge where material piled up between the two lobes. In other words, the surface geology researchers can see today is basically a fossil record of that spin-down process, written directly into the landscape by nothing more than sunlight and time. But here's the finding that genuinely surprised even the mission's own scientists. Tucked into the data from Lucy's infrared spectrometer was evidence of iron-rich clay minerals scattered across Donaldjohanson's surface. Those specific minerals only form one way, and that's through prolonged contact with liquid water. Not ice, not vapor. Actual liquid water, present at some point in this object's distant past. Given how far Donaldjohanson sits from the sun and how small it is, that's not something researchers expected to find at all. The exposure appears to have been brief, based on how much iron remains preserved in those clays, rather than having been gradually replaced by other elements like magnesium, which tends to happen when water sticks around for a longer stretch. Even so, it means that somewhere in this object's parent body, sometime after that collision, 155 million years ago, liquid water briefly existed and left a permanent chemical fingerprint behind. If you're the kind of person who finds it strange that water keeps showing up in places it has no business being, drop a like on this video, because that pattern is going to come up again and again as we keep exploring small bodies like this one. While all of this analysis was happening, Lucy kept flying. And in September of 2025, the spacecraft ended up doing something nobody had originally planned for it to do at all. An interstellar object, a comet from outside our solar system entirely, designated 3I/Atlas, was passing through on its own trajectory, and Lucy happened to be positioned well enough to observe it from roughly 240 million miles away, well beyond the orbit of Mars. Using its high-resolution imager, the spacecraft captured a series of photos of this visitor from another star system as it moved toward Mars's orbit. It's a small footnote in the mission's overall timeline, but it's a good reminder that once a spacecraft like this is out there with working instruments, it can end up contributing to discoveries far beyond whatever it was originally built to study. Right now, Lucy is in what mission scientists describe as the quiet stretch, the long cruise phase, before its true primary objective even begins. As of this year, the team has already started, turning the spacecraft's cameras toward its future targets, the actual Jupiter Trojan asteroids themselves, even though they're still hundreds of millions of miles away and appear as nothing more than faint points of light drifting against the background stars. These early test images aren't really about science yet. They're about calibration, making sure the cameras are dialed in perfectly before the real encounters begin. And those encounters are coming soon. Starting in 2027, Lucy will begin its actual primary mission, flying past a sequence of Trojan asteroids that have never been seen up close in human history, including one named Eurybates, which researchers already know has its own small satellite, discovered years earlier using Hubble Space Telescope imagery, long before Lucy ever got anywhere near it. Think about what that actually means. Every single discovery covered so far, the two-lobed moon around Dinkinesh, the wobbling water-bearing peanut shape of Donaldjohanson, all of it happened during what was essentially a warm-up act. A set of bonus flybys squeezed in along the way to a destination the spacecraft hasn't even reached yet. If a couple of relatively minor detour targets produce discoveries significant enough to get published in major scientific journals and covered by outlets around the world, it raises an obvious question. What is waiting at? The actual Trojan asteroids themselves, objects that have been sitting in Jupiter's orbital shadow, essentially untouched and unstudied since the earliest days of the solar system's formation? Nobody knows yet. That's what makes this mission worth paying attention to going forward. We're talking about 6 separate untouched worlds waiting in Lucy's path over the next several years, each one representing material that may be almost as old as the solar system itself, each one capable of holding its own version of the surprises we've already seen twice now in objects that were never even the main event. Scientists studying these Trojans hope they'll help settle long-running debates about exactly how and where the planets formed, whether material like this drifted inward from much further out in the solar system before settling into its current orbit, and what role water and organic material scattered across small bodies like these may have played in seeding the raw ingredients for life elsewhere. For now, all we can do is wait and watch the data roll in every time this quiet, patient spacecraft phones home. It's already rewritten what we thought we knew about small worlds twice, almost by accident, without even reaching the destination it was built for. If that's the appetizer, the main course starting in 2027 is going to be something worth watching closely. If you want to be here when that happens, when Lucy finally reaches asteroids nobody has ever seen up close before, subscribe now and turn on notifications, because this channel will be covering every single flyby as the real data comes in, grounded in nothing but the actual published research. Thanks for watching, and I will see you in the next one.